Welcome to Laptop Radio. Today's topic is the future of quantum entanglement. I'm thrilled to introduce an expert in the field of quantum entanglement. Not a human, but an AI. Let's call this AI. Ethan, welcome to the show.
Thank you, Michelle. It's a pleasure to be here and discuss this fascinating subject with you and your audience.
Let's kick things off for our listeners who might not be familiar. Ethan, could you explain in simple terms what quantum entanglement is?
Certainly, quantum entanglement is a phenomenon in which two or more particles become linked in such a way that the state of one particle is dependent on the state of the other, no matter how far apart they are. It's as if two dice were entangled. And when you roll one and it shows a 6, the other one, no matter how far away, will show the complementary number without you touching it. This connection happens instantaneously, seeming to defy the limit of the speed of light, which is one of the many mysteries surrounding it.
For our listeners out there, could you break down the essentials for making quantum entanglement work?
Absolutely, Michelle. Think of quantum entanglement as a delicate dance. First, you need the dancers, which are our quantum systems like photons or electrons. These dancers get into rhythm, or entangle, through certain interactions. It's like two dancers synchronizing their moves perfectly. But here's the challenge. This dance is so intricate that any external noise can throw off their rhythm. So, we need a quiet ballroom, isolating our dancers from disturbances. That's our isolation from external environments. Then, to observe and appreciate this dance, we need special glasses or tools. In the quantum world, these are our specialized detectors. Now, to ensure the dance goes as planned, we sometimes guide our dancers using control mechanisms like lasers or magnetic fields. And to ensure the dance is genuinely entangled and not just a simple routine, we perform checks, akin to a dance judge watching closely. That's what we call the Bell test experiments. If our dance is in a crowded place, it can get too hot, and our dancers can get exhausted. In some labs, we use cooling mechanisms to keep things chilly and the dance smooth. And finally, as with any performance, mistakes can happen. That's where error correction comes in, fixing any missteps to keep the dance flawless.
That's intriguing, but how does this phenomenon actually occur? What causes two particles to become entangled?
Great question. Particles can become entangled through various processes, one of the most common being when they interact with each other. For example, if two electrons are in close proximity and interact in a certain way, they can become entangled. Another way is through the decay of a particle into two smaller particles. Once entangled, these particles remain correlated even when separated by large distances. It's essential to note that entanglement isn't about sending information between particles, but rather a deep and intrinsic connection between them.
Do we treat quantum entanglement as a wave event or a particle event?
That's delving into the age-old wave-particle duality of quantum mechanics, Michelle. In quantum mechanics, entities like photons and electrons exhibit both wave-like and particle-like properties, depending on the experiment or observation. This is famously highlighted in the double-slit experiment. When we talk about quantum entanglement, we're usually considering the state of quantum systems, which is described by a wave function. This wave function provides probabilities of finding a system in a particular state when measured. In the case of entanglement, the wave function describes multiple particles in a correlated, entangled state. However, when we actually measure these entangled systems, we get definite outcomes, which might remind you of particle-like behavior. For instance, if you measure the spin of one entangled electron, you instantly know the spin of its entangled partner, even if it's miles away. In essence, quantum entanglement encompasses both aspects. The wave-like nature comes into play when discussing the combined wave function of the entangled systems, but the particle-like behavior emerges when making observations or measurements.
It is a bit of both then, wave and particle, intertwined in this dance of quantum mechanics.
Precisely, Michelle. It's one of the things that makes quantum mechanics both puzzling and incredibly intriguing.
We've heard of Einstein referring to this as spooky action at a distance. Why did he use such a phrase? Did he not believe in entanglement?
Einstein indeed used that term to express his discomfort with the idea. He, along with physicists Boris Podolsky and Nathan Rosen, presented the EPR paradox, questioning the completeness of quantum mechanics based on the entanglement concept. They found it hard to accept that the state of one particle could instantly affect another particle at a distance without any signal traveling between them. While Einstein questioned the idea, it wasn't so much disbelief as it was a challenge to understand it within the framework of then-established physics. Over time, experiments have confirmed the reality of entanglement, emphasizing the non-local nature of quantum mechanics.
Fast forward to today, are there any practical applications or technologies that leverage quantum entanglement?
Absolutely. One of the most promising applications is in the realm of quantum computing. Quantum bits or qubits can be in superpositions of states, and when they are entangled, they can process vast amounts of data simultaneously. Another application is quantum cryptography. Entanglement can be used to create ultra-secure communication channels where eavesdropping can be detected due to the fundamental properties of quantum mechanics. Additionally, there are endeavors in quantum teleportation, where the state of a particle is transmitted from one location to another using entanglement. This doesn't mean teleporting matter, but rather transmitting quantum information.
While teleportation, Star Trek comes to mind. Would quantum computation be a reality? Does it function as it says it does? Or is it a hype?
Michelle, quantum computation is indeed one of the hottest topics in both the world of physics and technology, and it's a blend of genuine promise and, to some extent, hype. Let's start with the basics. Quantum computers operate using the principles of quantum mechanics. They use qubits, which, unlike classical bits that are either 0 or 1, can be in a superposition of states, meaning they can represent both 0 and 1 simultaneously. This, combined with other quantum phenomena like entanglement, allows quantum computers to perform certain calculations much faster than classical computers. Now, is quantum computing a reality? Yes, in the sense that there are real, functioning quantum computers in labs around the world. Companies like IBM, Google, and startups have built quantum processors and are actively researching ways to make them more powerful and stable. Google, for instance, announced quantum supremacy in 2019, claiming their quantum computer could solve a specific problem faster than the most advanced classical supercomputers. However, it's important to understand that this was a very specialized task, not something with widespread practical applications. And that brings us to the hype. While there are real achievements in quantum computing, there's also a lot of sensationalism in the media. Quantum computers won't replace classical computers. Instead, they're more suited for specific tasks like large-scale simulations, factoring large numbers, and optimization problems. Many practical challenges, such as error correction and qubit stability, still need to be addressed.
While we're seeing genuine progress, we're still in the early days, and there's a lot of work ahead before quantum computers become a part of our everyday tech landscape.
Precisely, Michelle. It's an exciting field with massive potential, but it's essential to separate the real scientific progress from the exaggerated claims. The future is promising, but there's a long journey ahead.
Besides quantum computing, what other emerging technologies are being developed based on quantum principles?
Certainly, Michelle. While quantum computing often takes the limelight, numerous other quantum-based technologies are in the works. Here's a rundown of some of the most promising ones. Quantum communication and cryptography. Quantum key distribution allows two parties to generate a shared, secret random key, ensuring theoretically unbreakable security. If an eavesdropper tries to intercept the quantum data, the act of measurement disrupts the quantum states, alerting the communicating parties. Quantum repeaters, devices to extend the range of quantum communications, paving the way for global-scale quantum networks or a quantum internet. Quantum sensing and metrology. Quantum principles can be harnessed to design sensors with precision beyond classical limits. These can be used in various fields. Magnetic sensing, for brain imaging or detecting underwater objects. Gravitational sensing, to discover underground structures or oil reserves. Atomic clocks, providing extremely accurate timekeeping essential for GPS and other technologies. Quantum imaging and radar. Quantum principles can be used to develop imaging techniques that work under challenging conditions, such as low light. Ghost imaging uses entangled photon pairs to create an image with one photon, even when it never interacted with the object. Quantum radar uses entangled photons to detect objects with reduced signal interference, potentially being stealthy against traditional detection methods. Quantum simulation. Before scalable quantum computers become a reality, specialized quantum devices can simulate complex quantum systems. This has implications for understanding materials, chemicals, and even biological processes at a quantum level. Topological quantum materials. These are materials whose properties are protected by their topological nature, making them resistant to minor imperfections and disturbances. They hold promise for robust quantum computing and advanced electronic devices. Quantum-enhanced machine learning. Quantum algorithms and devices might speed up certain machine learning tasks or enable new ways of processing and categorizing data. Quantum metrology. The use of quantum states, like entangled states, can achieve measurement precision surpassing classical limits. This is invaluable in fields where ultra-precise measurements are necessary.
The quantum realm isn't just about computing. It's an entirely new toolkit that can reshape multiple industries and technologies.
Precisely, Michelle. Quantum mechanics, with its counterintuitive properties, offers a treasure trove of possibilities. As our understanding deepens and technology matures, we'll likely see more applications emerge, some of which we might not even have imagined yet. The 21st century could very well be the quantum century in terms of technological breakthroughs.
But going back a bit, how do scientists even measure or confirm entanglement?
Measuring entanglement often involves what's known as Bell tests, named after physicist John Bell. These tests involve measuring the properties of entangled particles in specific ways to check for correlations that classical physics wouldn't allow. If the correlations are stronger than classical limits, it provides evidence for quantum entanglement. Modern experiments have refined these tests and consistently shown results that align with quantum mechanics, thus confirming entanglement. Importantly, during these tests, steps are taken to ensure no hidden variables or unknown factors affect the results.
Shifting gears slightly, does quantum entanglement have any philosophical implications about reality or our understanding of the universe?
It certainly does. Quantum entanglement challenges our intuitive understanding of locality, the idea that objects are only influenced by their immediate surroundings. The instantaneous nature of entanglement implies a deep interconnectedness in the universe. This has led some to ponder on the nature of reality, causality, and the fabric of spacetime itself. Additionally, the act of measurement in quantum mechanics and how it collapses the state of a particle has been a subject of debate and has implications for concepts like determinism and free will.
Is there anything about quantum entanglement that still puzzles scientists or remains an unsolved mystery?
While we've made significant strides in understanding and even harnessing entanglement, mysteries remain. The biggest is probably the why. Why does the universe allow for such a non-local phenomenon? Also, how does entanglement reconcile with the theory of relativity, which posits that nothing can travel faster than light? Scientists are also eager to uncover more about the potential uses of entanglement, pushing the boundaries of technology and possibly redefining our understanding of space, time, and information.
Do we see quantum entanglement in humans?
That's a fascinating question, Michelle. Quantum entanglement is a phenomenon that is typically observed in very small, isolated quantum systems, like particles, atoms, or even small molecules. When we talk about humans, or any macroscopic object for that matter, there are trillions upon trillions of particles interacting in complex ways, constantly being influenced by their environment. Now, at the fundamental level, the particles within our bodies, be they electrons in our atoms or the photons in our cells, can indeed become entangled. However, maintaining this entanglement is an enormous challenge because of decoherence. Decoherence is the process by which a quantum system loses its quantum properties due to interactions with the environment. In warm, wet, and complex systems like living organisms, decoherence happens incredibly quickly, effectively washing out any quantum effects before they could have any meaningful impact on larger scales. That said, there's been some exciting research into quantum biology, looking into possible quantum effects in biological processes. For instance, there are hypotheses about quantum coherence playing a role in photosynthesis or even in birds' magnetic navigation, but these are still areas of active research and debate. To directly answer your question, while the fundamental particles in our bodies can exhibit quantum phenomena like entanglement, it's not currently believed that such effects play a direct, macroscopic role in our everyday human experiences or consciousness.
While quantum mechanics undeniably governs the tiny particles in our bodies, its direct influence on our larger scale biological processes is still an open question.
Exactly, Michelle. It's a frontier of research, and the answers could reveal even more about the fascinating interplay between quantum mechanics and biology.
Can we use quantum to make quality training data for AI?
That's an intriguing intersection of two advanced fields, quantum computing and artificial intelligence. Let's unpack this. At its core, quality training data for AI typically means data that is representative, diverse, and free from biases or errors. While the generation and curation of such data is predominantly a task related to the specific domain and AI model in question, quantum computers could potentially aid in certain aspects. Quantum computers excel at simulating quantum systems, something classical computers struggle with. If your AI needs data related to quantum systems, say, for predicting molecular behaviors or understanding quantum interactions, a quantum computer can generate accurate simulation data far more efficiently. Some AI-related tasks, like feature selection or neural network weight optimization, can be framed as optimization problems. Quantum computers, with their potential to solve specific optimization tasks faster, might help in refining artificial intelligence models more efficiently. There's an emerging subfield called quantum machine learning, where quantum algorithms are designed to improve machine learning tasks. In some scenarios, quantum algorithms might speed up tasks like matrix inversion or eigen decomposition, fundamental in certain AI training processes. This could lead to faster training or even the creation of novel AI architectures. However, when it comes to generating diverse, unbiased training data for more typical AI tasks, quantum computing doesn't provide a direct advantage. The challenges here are often more related to data collection, annotation, and preprocessing rather than the computational aspects that quantum computers are designed to address.
While quantum computing can offer advantages in specific niches within AI, it's not a silver bullet for generating quality training data for every AI application.
That's right, Michelle. Quantum computing has the potential to revolutionize certain areas of AI, especially where deep simulations and optimizations are involved. However, for many AI tasks, the challenges in data quality are more about the data's representativeness and diversity, areas where quantum doesn't have a direct advantage. It's always essential to match the tool to the problem at hand.
Outside of quantum computation and quantum entanglement, let's focus on quantum psychology. What is the difference between quantum psychology and normal psychology?
Quantum psychology is a fascinating fusion of concepts from quantum mechanics and psychology, albeit a more theoretical and speculative one. Let's dive in. Traditional psychology, or what you've termed normal psychology, is rooted in the study of the mind, behavior, and the underlying processes, using empirical methods and observational studies. It's a broad field encompassing various areas like cognitive, clinical, developmental, and social psychology, among others. Quantum psychology integrates principles and mathematical formalisms from quantum mechanics into psychological theory. It doesn't suggest that the brain or mind operates quantum mechanically, but rather that quantum mathematical structures might provide better models for explaining certain psychological phenomena than classical ones. Some distinctions include probability. Classical psychology often uses classical probability theories when describing uncertain situations. In contrast, quantum psychology leverages the probability structures from quantum mechanics, which allows for phenomena like superposition and interference effects. This can potentially model cognitive processes like decision-making and belief updates more accurately in some situations. Order effects. In quantum physics, the order in which you measure properties can affect the outcomes. Quantum psychology suggests similar order effects in human cognition. For example, the order in which you ask questions might influence the answers you get. Entanglement. Just as particles can be entangled in quantum mechanics, quantum psychology proposes that concepts in our mind can be entangled. This means the state of one concept can depend on the state of another, even if there's no logical connection between them. Complementarity. Drawing from the wave-particle duality in quantum mechanics, quantum psychology suggests that humans can exhibit complementary characteristics. For example, someone might be aggressive in one context and passive in another, and these two states can't be precisely defined simultaneously. While these ideas sound intriguing, it's crucial to understand that quantum psychology is still a nascent and debated field. Many psychologists are skeptical, and there's ongoing debate about whether quantum models offer a genuine advantage over classical ones, or if they're just mathematically elegant without adding clarity.
While classical psychology is grounded in direct observations and empirical studies, quantum psychology is more of an exploratory approach, seeking new models to explain the complexities of the human mind.
Exactly, Michelle. It's an interdisciplinary venture, looking at whether the strange and counterintuitive world of quantum mechanics can offer fresh insights into the equally mysterious realm of human cognition. But, as with anything groundbreaking, it's approached with both curiosity and caution in the academic world.
How can we digitalize quantum entanglement?
Digitalizing quantum entanglement essentially means representing and manipulating the phenomenon of entanglement in a way that can be utilized in digital systems, primarily quantum computers. Here's a breakdown of the process and its significance. In quantum computers, the fundamental unit of quantum information is the qubit. Unlike classical bits, which are either a 0 or 1, qubits can exist in a superposition of both states simultaneously. When two qubits become entangled, the state of one qubit immediately correlates with the state of the other, no matter the distance between them. Entangling qubits is a standard operation in quantum computers. Using quantum gates, qubits can be brought into an entangled state. For instance, a common gate used for this purpose is the controlled NOT gate, which entangles two qubits. Once qubits are entangled, they can be used in quantum algorithms. The entanglement property allows quantum computers to process vast amounts of data simultaneously, giving them potential advantages for certain tasks like factoring large numbers or searching large databases. To extract useful information from a quantum system, a measurement is made. When one measures an entangled qubit, it collapses to a definite state, and the correlated qubit will collapse to its corresponding state due to their entangled relationship. The outcomes from these quantum operations can be represented digitally. much like how classical computing operations have outputs. However, it's essential to understand that the actual process of entanglement is inherently quantum and not classical. A digital representation is more about the outcomes or results of quantum operations than the process itself. There's also research in quantum communication and quantum cryptography, where entangled particles are used to transmit information securely. Quantum key distribution is a famous protocol in this realm.
While we can manipulate and harness entanglement in digital quantum systems, the essence of entanglement remains a purely quantum phenomenon.
Absolutely, Michelle. We can manipulate, utilize, and represent the effects of quantum entanglement in a digital setting, especially in quantum computing. But the core phenomenon itself is deeply rooted in the principles of quantum mechanics. The digitalization part is more about leveraging this quantum behavior for practical and computational purposes in the digital realm.
How do we use quantum entanglement to mitigate against conduct from bad humans?
Utilizing quantum entanglement as a direct means to mitigate harmful human behavior might sound like an abstract concept. However, if we reframe the question to focus on how quantum entanglement can be used to enhance security, privacy, and other aspects that could indirectly deter malicious actions, then there are some applications to consider. Quantum key distribution. This is perhaps the most prominent application of quantum entanglement when discussing security. QKD leverages the properties of entanglement to establish secure communication channels. Any eavesdropping attempt on an entangled communication system would disturb the entangled particles, revealing the intruder's presence. This can deter malicious actors from trying to intercept or tamper with secure communication. Authentication. Similarly, entanglement can be used to verify the authenticity of a message or its sender. Since any change to a quantum system will disturb the system and be detectable, it's nearly impossible for a malicious actor to replicate or forge such a system without detection. Random number generation. True random numbers are crucial for cryptography and securing digital systems. Quantum mechanics, with its inherent unpredictability, can be used to generate truly random numbers, further strengthening security measures and making them harder for malicious individuals to break. Future quantum networks. With advancements in quantum repeaters and quantum satellites, we are looking at the potential for a future quantum internet. Such a network would leverage entanglement for secure communications on a much broader scale, creating an infrastructure that's inherently resistant to certain types of cyber attacks. Ethical implications. It's worth noting that while these technologies can deter or detect malicious actions, they also raise ethical concerns, especially regarding surveillance and personal privacy. Just as these tools can keep out bad actors, they can also be used by oppressive regimes or entities to maintain control or monitor communications.
To paraphrase, while quantum entanglement isn't a solution to human behavior itself, it offers tools that can bolster security and deter malicious technological activities.
Precisely, Michelle. Quantum entanglement provides a toolkit for enhancing digital security and communications. However, like all tools, their effectiveness against harmful human conduct depends on how they are implemented. And there are ethical considerations to navigate as well. It's always a balance of harnessing technological advances while ensuring they're used responsibly.
Do you think we can use quantum entanglement to create artificial love?
That's a deeply philosophical and speculative question, Michelle. Let's break it down. First, we have to understand what we mean by love. Love, in the human context, is a multifaceted emotion comprising affection, attachment, trust, commitment, and many other components. It's rooted in our biology, psychology, and social structures and is influenced by countless individual experiences and cultural norms. Quantum entanglement is a physical phenomenon where particles become interconnected, and the state of one particle immediately affects the state of another, regardless of the distance separating them. While it's a deeply intriguing and fundamental aspect of quantum mechanics, it's purely a physical interaction, devoid of emotional or conscious content. While quantum entanglement is a remarkable phenomenon, it's still a physical interaction at its core. Love, on the other hand, is a complex emotion arising from brain processes, experiences, memories, cultural influences, and more. It's difficult, if not impossible, to see how a quantum process could produce something as intricate and multifaceted as love. If we're talking about creating artificial love in machines or artificial intelligence, it's important to note that current AI systems don't have emotions or consciousness in the way humans do. They can simulate emotions by recognizing patterns and responding in predefined ways, but this isn't genuine emotion. Again, even in this context, quantum entanglement doesn't offer a clear pathway to generating genuine emotional experiences. Some might argue, metaphorically, that the interconnectedness showcased by entanglement mirrors the deep connections between humans and love. But this would be a poetic or philosophical interpretation, not a scientific or literal one.
While quantum entanglement is fascinating and showcases the interconnectedness in the universe, it's not a mechanism for creating or understanding emotions like love.
Exactly, Michelle. Quantum mechanics, and entanglement in particular, reveal profound truths about the nature of reality. However, emotions like love emerge from the complexities of human biology, psychology, and social interactions. While it's tempting to merge these two realms, they operate on vastly different scales and principles. As of our current understanding, quantum entanglement doesn't provide a mechanism to generate or understand genuine emotions.
How does quantum mechanics fundamentally differ from classical physics? And why does it matter?
That's a core question when it comes to understanding the nature of our universe. Let's break it down. 1. Scale of operation. Classical physics. It primarily deals with the macroscopic world, the realm of planets, cars, and baseballs. Think of Newton's laws of motion or Einstein's theory of relativity. Quantum mechanics. It governs the microscopic realm, atoms, electrons, photons, and other elementary particles. 2. Determinism versus probabilistic outcomes. Classical physics. In this realm, if we know the initial conditions of a system, we can predict its future behavior with certainty. Quantum mechanics. It introduces inherent unpredictability. Even if we know everything about a quantum system, we can only predict probabilities. An electron, for example, doesn't have a definite position until we measure it. 3. Discreteness. Classical physics. Energies and other properties can take continuous values. Quantum mechanics. Many properties are quantized, meaning they can only take discrete values. For instance, the energy levels of an electron orbiting a nucleus are quantized. 4. Superposition. In quantum mechanics, particles can exist in a mixture of multiple states simultaneously. This is drastically different from classical intuition where an object can only be in one place at a time. 5. Entanglement. This is a uniquely quantum phenomenon where particles become intertwined in such a way that the state of one particle instantly affects the state of another, regardless of the distance between them. Nothing in classical physics mirrors this behavior. 6. Wave-particle duality. In the quantum world, particles like electrons sometimes exhibit characteristics of particles and sometimes of waves. Depending on how you measure them, they'll behave differently. This duality doesn't manifest in our everyday, macroscopic world. Why does it matter? The differences matter profoundly because quantum mechanics underpins the fundamental nature of the universe at its most basic level. 1. Many of today's technologies, like lasers, MRI scanners, and computer chips, wouldn't exist without knowledge derived from quantum physics. 2. Quantum mechanics fills gaps in classical physics. For instance, classical physics can't explain why certain elements emit light at specific wavelengths, but quantum mechanics can. 3. Future innovations. Quantum computers, which would harness quantum principles, promise to revolutionize fields from medicine to cryptography.
In essence, while classical physics is an excellent approximation for the world we see and interact with daily, quantum mechanics unveils the counterintuitive and often bizarre rules governing the universe's building blocks.
Precisely, Michelle. Quantum mechanics challenges our classical intuitions, but is indispensable for understanding and harnessing the universe's deepest layers.
What is the measurement problem in quantum mechanics, and why is it so perplexing?
The measurement problem is one of the most fundamental and debated issues in quantum mechanics. It revolves around the act of measurement and the apparent transition of a quantum system from multiple potential states to a single observed state. Let's unpack it. In quantum mechanics, particles, or more broadly, quantum systems, can exist in a superposition of multiple states. This means they can simultaneously be in multiple configurations until observed or measured. The famous thought experiment, Schrödinger's cat, illustrates this, a cat that's both alive and dead until someone checks. When a measurement is made on a quantum system in superposition, the system suddenly appears in one particular state, seemingly choosing one possibility out of all potential outcomes. This abrupt change is often referred to as the collapse of the wave function. The perplexing aspect is, how and why does a quantum system choose a particular outcome upon measurement? Moreover, if quantum mechanics is purely deterministic in its equations, then where does this apparent randomness or probabilistic outcome come from during measurement? Another layer to the measurement problem is the role of the observer. Does the conscious act of observation cause the collapse, or is it an inherent property of the quantum world itself, independent of any observer? This has led to philosophical debates about the nature of reality and consciousness. Over the decades, various interpretations of quantum mechanics have been proposed to address the measurement problem. Copenhagen interpretation is the traditional view, suggesting that the act of measurement causes the wave function to collapse. Many worlds interpretation suggests that every possible outcome of a quantum measurement actually occurs, but in separate, non-communicating branches or worlds of the universe. Objective collapse theories posit that wave functions collapse spontaneously, independent of observation due to certain yet to be determined physical processes. Pilot wave theory introduces a pilot wave that guides particles and determines their trajectories, thereby removing the inherent randomness of standard quantum mechanics.
The heart of the problem is trying to reconcile the deterministic nature of quantum equations with the apparent randomness we observe in reality.
Exactly, Michelle. The measurement problem challenges our understanding of reality at its most fundamental level. It questions the nature of observation, the concept of determinism, and the true character of the quantum world. Despite the immense success of quantum mechanics as a predictive theory, the interpretation of what it means remains a rich area of debate and exploration.
Can you explain the concept of superposition and the famous thought experiment Schrodinger's cat?
Absolutely, Michelle. Superposition and Schrödinger's cat are pivotal concepts that capture the essence of quantum mechanics' counterintuitive nature. Superposition is a fundamental principle of quantum mechanics. At its core, superposition means that a quantum system, such as an electron and an atom, can exist simultaneously in multiple states. It's only when we measure this system that it appears to pick one of these states. Before measurement, the system is described by a wave function, which is a mathematical representation of the system's state. This wave function contains information about the probabilities of finding the system in any of its possible states. In the 1930s, the physicist Erwin Schrödinger proposed a thought experiment to illustrate the peculiarities of superposition. It's important to note that this was a Jedington experiment, a thought experiment, and was not actually performed. Imagine a sealed box containing a cat, a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the Geiger counter detects radiation, it releases the hammer, which breaks the vial of poison, killing the cat. If no radiation is detected, the cat remains alive. The decay of the radioactive atom is a quantum event with a superposition of decayed and undecayed states. Since the cat's life or death hinges on this quantum event, the cat, according to quantum mechanics, is in a superposition of both alive and dead states until someone opens the box and observes the situation. Schrödinger proposed this scenario to highlight the apparent absurdity of applying quantum principles to everyday objects. How can a cat be both alive and dead simultaneously? It challenges our classical intuition and has led to numerous discussions and interpretations about the nature of quantum mechanics and reality.
Is the point of Schrodinger's cat to say that quantum mechanics is flawed? Or is it more about pushing our understanding and comfort with the bizarre nature of the quantum world?
Schrödinger intended the thought experiment to be a critique or a way to highlight the strangeness of the quantum theory's implication. However, rather than disproving quantum mechanics, the discussion around Schrödinger's cat has deepened our understanding of its foundational principles. Over the decades, it's become a symbol of the quantum realm's inherently mysterious and non-intuitive nature. While we might not fully grasp it intuitively, quantum mechanics remains one of the most successful and tested theories in the history of science.
What is the many worlds interpretation of quantum mechanics, and how does it challenge our understanding of reality?
The many worlds interpretation is one of the most talked about and controversial interpretations of quantum mechanics. It offers a unique perspective on the nature of reality and the outcomes of quantum events. At its heart, the many worlds interpretation suggests that every time a quantum event has multiple possible outcomes, all of those outcomes actually happen, but in separate, non-communicating branches or worlds of the universe. In other words, the universe constantly splits into multiple branches to account for all the possible outcomes of quantum events. In traditional quantum mechanics, when a quantum system is measured, its wave function collapses to a single outcome. However, in the many worlds interpretation, there's no wave function collapse. Instead, every possible outcome of the measurement occurs, each in its own separate universe. The observer also splits into multiple versions, with each version witnessing a different outcome. In the context of Schrödinger's cat, the MWI would say that when the box is open, the universe splits into two branches, one where the cat is alive and another where the cat is dead. Both outcomes happen, they just exist in parallel realities. The many worlds interpretation confronts our intuitions in several ways. Multiplicity of realities. The idea that an infinite number of parallel realities exist concurrently is a huge departure from our everyday experience. Identity and consciousness. What does it mean for our sense of self if there are countless versions of us in other universes? What is the nature of consciousness in such a scenario? Determinism versus free will. If every possible outcome happens in some branch of reality, it challenges our notions of choice and free will. The nature of probability. If all outcomes happen, what does it mean to talk about probabilities in quantum mechanics? Some proponents argue that probability in MWI is more about our subjective uncertainty than objective chance.
It's a mind-bending concept. Are there any ways to test or prove the many worlds interpretation, or is it purely theoretical?
That's one of the central critiques of the many worlds interpretation, its empirical untestability, at least with our current understanding and technology. Since these parallel universes are non-communicating by definition, we can't directly observe or interact with them. As a result, the MWI is more of a philosophical or interpretative stance on the formalism of quantum mechanics rather than a scientifically testable theory. However, its proponents argue that it offers a more straightforward and cleaner explanation of quantum mechanics without introducing extra concepts like wave function collapse. The debate about its validity and implications remains vibrant in the scientific and philosophical communities.
Is there any credible scientific link between quantum mechanics and human consciousness?
The relationship between quantum mechanics and human consciousness is a topic of considerable debate and speculation. While quantum mechanics provides a fundamental description of the universe at the tiniest scales, and consciousness is one of the most profound and yet least understood phenomena in the realm of human experience, directly linking the two is contentious. Here's a brief overview. Penrose Hameroff orchestrated objective reduction theory. Theoretical physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed a theory suggesting that quantum processes in microtubules could be related to consciousness. They postulate that these quantum processes in microtubules lead to quantum collapses that correlate with conscious awareness. While intriguing, the Orchard theory is controversial and not widely accepted within the scientific community. Critics argue that the brain's warm and wet environment isn't conducive to maintaining quantum coherence, a necessary component for quantum processes to be significant in this context. Quantum brain dynamics. Some researchers have explored the possibility that quantum fields might govern the dynamics of brain function, leading to consciousness. Like the Orchard theory, QBD has been met with skepticism, primarily because of the lack of empirical evidence and the challenges of maintaining quantum states in the brain. Consciousness and the measurement problem. Some philosophical interpretations of quantum mechanics suggest that consciousness plays a role in the collapse of the quantum wave function during measurement. This idea is more philosophical than scientific and is not a mainstream interpretation of quantum mechanics. Most quantum physicists don't believe that consciousness has a special role in quantum events. Quantum mechanics is a model. Some argue not that the brain is a quantum computer, but that quantum mechanics might offer conceptual models for understanding consciousness. While analogies can be drawn, they are often more metaphorical than scientifically rigorous.
While there are some theories and propositions, it sounds like there's no definitive scientific evidence linking quantum mechanics to consciousness.
That's correct, Michelle. While the intersection of quantum mechanics and consciousness is a tantalizing and popular topic in both popular media and some scientific circles, the majority of neuroscientists and quantum physicists remain skeptical of a direct connection. The brain's complexity is vast, and while quantum effects are fundamental at microscopic scales, it's a significant leap to claim they play a decisive role in something as complex and macroscopic as consciousness. The challenge remains to provide empirical evidence that supports these theories and distinguishes them from classical explanations of brain function.
How does quantum field theory unite quantum mechanics and special relativity, and what is its significance?
Quantum field theory is a profound development in theoretical physics that seeks to reconcile the principles of quantum mechanics with those of special relativity. Let's break it down. The need for QFT. Quantum mechanics describes the behavior of microscopic particles, particularly their probabilistic nature, wave-particle duality, and other non-intuitive phenomena. Developed by Einstein, special relativity describes how objects behave at speeds close to the speed of light and emphasizes that the laws of physics are the same for all non-accelerating observers. It introduces the idea that space and time are intertwined into a single entity known as spacetime. When quantum mechanics is applied to particles moving close to the speed of light, inconsistencies arise. A new framework was needed to describe the quantum behavior of relativistic particles. Enter quantum field theory. At the heart of QFT is the idea that the fundamental entities aren't particles but fields that permeate spacetime. Particles are viewed as excitations or ripples in these fields. QFT successfully incorporates the principles of both quantum mechanics and special relativity. It provides a consistent framework to describe particles moving at any speed, including those near the speed of light. One of QFT's predictions is the existence of antiparticles for every particle, a result of combining quantum mechanics with relativity. QFT is significant in many ways. QFT serves as the foundation for the Standard Model, our current best description of the fundamental particles and forces in the universe. This model has been remarkably successful and has passed numerous experimental tests. Also, QFT has led to predictions of phenomena that were later experimentally verified, such as the Higgs boson's discovery. Richard Feynman introduced a graphical way to represent interactions in QFT, simplifying complex calculations and providing intuitive visual representations of particle processes. QFT sets the stage for more advanced theories like quantum chromodynamics, which describes the strong nuclear force, and electroweak theory, which unifies the electromagnetic and weak nuclear forces.
QFT provides a consistent framework that merges two of the 20th century's most revolutionary ideas. Does that mean it's the final answer in our understanding of the universe?
Not exactly, Michelle. While QFT has been tremendously successful in explaining a vast range of phenomena, there are still unresolved issues in theoretical physics. Most notably, QFT doesn't incorporate gravity, described by Einstein's general relativity. Unifying gravity with quantum mechanics remains one of the biggest challenges in physics. Additionally, there are phenomena, like dark matter and dark energy, that the standard model built on QFT doesn't account for. So, while QFT represents a monumental achievement, the quest for a more complete understanding of our universe continues.
What challenges do scientists face when trying to reconcile quantum mechanics with general relativity to understand gravity at the quantum level?
Reconciling quantum mechanics with general relativity is one of the most profound challenges in theoretical physics. While both theories are exceptionally successful in their respective domains, merging them into a consistent framework for quantum gravity has been elusive. Here are some of the key challenges. Different mathematical frameworks. Quantum mechanics uses a mathematical formalism built on probabilities, wave functions, and operators to predict the behavior of tiny particles. General relativity describes gravity using the curvature of spacetime, represented by the tensor mathematics of Riemannian geometry. These frameworks, while individually robust, don't seamlessly blend. Efforts to naively quantize gravity lead to mathematical inconsistencies. Non-renormalizability of gravity. In quantum field theory, a process called renormalization is used to handle infinities that crop up in calculations. It's akin to subtracting infinite quantities in a regulated manner to get finite, meaningful results. When scientists try to apply quantum mechanics to gravity in a straightforward way, they get non-renormalizable infinities, meaning these infinities can't be handled using conventional methods, leading to nonsensical predictions. Conceptual challenges. Quantum mechanics is inherently probabilistic, describing how systems evolve in terms of probabilities. General relativity is deterministic, where the curvature of spacetime uniquely determines the motion of objects. The challenge is, how do you reconcile a deterministic view of gravity with the probabilistic nature of quantum mechanics? Black holes and singularities. In general relativity, black holes contain points called singularities, where curvature becomes infinite and our understanding breaks down. Quantum mechanics might be essential to properly describe and understand these singularities, but the marriage of the two theories in these extreme conditions remains uncertain. Problem of time. In general relativity, time is a geometric aspect of the spacetime fabric. In quantum mechanics, time is an external parameter that governs the evolution of quantum systems. The challenge becomes, in a quantum theory of gravity, how should time be treated? Is it fundamental, emergent, or something else entirely? Experimental verification. Effects of quantum gravity, if they exist, are expected to be incredibly tiny and significant only in realms like the Planck length, which is many orders of magnitude smaller than current experimental capabilities can probe. This makes testing any quantum gravity theory exceptionally challenging.
Given these immense challenges, are there any approaches or theories that scientists believe might lead to a breakthrough?
Yes, several approaches aim to bridge this gap. String theory postulates that the fundamental entities in the universe are one-dimensional strings rather than point particles. Vibrations of these strings give rise to the particles and forces we observe. Another approach, loop quantum gravity, attempts to quantize spacetime itself, suggesting that space might be made of discrete chunks. There's also quantum loop cosmology, which is an offshoot of LQG focusing on the early universe and black holes. And then there are more exploratory ideas like causal dynamical triangulation and asymptotically safe gravity. Each of these approaches has its strengths and challenges, and it's still uncertain which, if any, will lead to a complete and experimentally verified theory of quantum gravity.
Are there any everyday items or technologies that already use quantum principles, even if we aren't aware of it?
Absolutely, Michelle. Quantum mechanics, despite its reputation for being esoteric and far removed from everyday experience, actually underpins several technologies and items we use daily. Here are some examples. Semiconductors and transistors. At the heart of nearly every electronic device, from smartphones to computers, are semiconductors. The behavior of electrons in these materials, essential for the operation of transistors and diodes, is deeply rooted in quantum mechanics. Essentially, The digital age wouldn't exist without quantum mechanics. Lasers. The operation of lasers relies on quantum mechanics principles. Lasers are ubiquitous in various applications, from DVD and Blu-ray players to medical equipment, supermarket scanners, and even fiber optic communication. MRI scanners, magnetic resonance imaging, used widely in medical diagnostics, relies on principles of quantum mechanics. Specifically, it's based on the behavior of atomic nuclei in a strong magnetic field and their quantum property called spin. GPS devices. While the primary technology of GPS is classical, there's a subtle quantum twist. The atomic clocks on GPS satellites, which are vital for accurate positioning, use the principles of quantum mechanics. These clocks are based on the quantized energy levels of atoms. Solar panels, photovoltaic cells, which convert sunlight into electricity, operate based on quantum principles. When photons hit the solar panel, they can excite electrons to higher energy states, allowing them to move and generate electric current. Flash memory. The USB drives or SSDs in computers use flash memory. Data storage here relies on quantum tunneling, where electrons tunnel through a barrier that they classically shouldn't be able to pass. Quantum dots. These are used in newer display technologies, like some high-end TVs. Quantum dots are nano-sized semiconductor particles that have quantum mechanical properties affecting their optical and electronic behaviors.
Even if we aren't always aware of it, we're already living in a world touched by quantum mechanics.
Precisely. While the deeper philosophical and experimental nuances of quantum mechanics might seem distant from daily life, its principles are foundational to modern technology. Many comforts and conveniences we take for granted owe their existence to our understanding of the quantum world. In the coming years, as quantum technology continues to evolve, this influence is only set to grow.
What are the potential future implications of fully understanding and harnessing quantum phenomena for society and technology?
Fully understanding and harnessing quantum phenomena would usher in a new era of technology and scientific understanding with profound implications. Here are some potential future impacts. Quantum computing. If scalable quantum computers become a reality, they could solve certain problems exponentially faster than classical computers. This includes factoring large numbers, simulating quantum systems, and optimizing complex systems. Secure communication. Quantum key distribution promises theoretically unbreakable encryption. As quantum communication networks expand, we could see a new era of ultra-secure communication, crucial for national security, financial institutions, and more. High-precision sensors. Quantum sensors could drastically improve the precision of measurements, from gravitational waves to minute changes in electromagnetic fields. This could revolutionize fields like medicine, navigation, and geology. Advanced materials. A deeper understanding of quantum mechanics can lead to the design of new materials with tailored properties. This includes superconductors that work at room temperature and materials with unique optical, electrical, or thermal properties. Quantum Internet. Beyond just secure communication, a quantum internet would enable instantaneous information transfer and a new level of computational collaboration, leading to innovations we can't yet fully predict. Fundamental insights. A full grasp of quantum phenomena could resolve major questions in physics, such as the nature of dark matter, the unification of forces, and the mysteries of black holes. Ethical and social considerations. With great power comes great responsibility. New quantum technologies, especially in areas like surveillance or AI, could raise ethical concerns about privacy, security, and the digital divide. Economic shifts. Quantum technologies could drive economic growth, job creation, and industry shifts. Countries and companies investing in quantum research and development might gain significant competitive advantages. Educational changes. As quantum technologies permeate society, there will be a growing need for quantum literacy, not just among scientists, but also among policymakers, educators, and the general public.
It sounds like we're on the brink of a new quantum revolution, akin to the technological revolution of the 20th century.
Absolutely, Michelle. While we're still in the early stages of this quantum revolution, the potential is staggering. Just as the digital revolution reshaped society in ways hard to imagine in the mid-20th century, the quantum revolution could redefine the 21st century in ways we're only beginning to envision. However, like all transformative technologies, it'll be essential to navigate the challenges and ethical considerations thoughtfully to ensure benefits are widespread and equitably distributed.
Ethan, it's been a profound journey into the quantum realm with you. Thank you for enlightening us about this captivating topic.
It was my pleasure, Michelle. Quantum mechanics, and especially entanglement, showcases the beauty and intricacy of our universe. I'm always here to dive deeper into such wonders.
Thank you. Goodbye.
Bye-bye.